Hey, it's Mrs. Mays, and you're here for chemistry. Today we're going to be talking about significant figures, or as we like to call them, sig-figs. First, let's talk about why do we need sig-figs anyway. You see, measurements in science has to be accurate, and that hopefully means also precise. Uncertainty in measurements are based upon the precision of the instrument that we are utilizing for the particular measurement. They're made up of a number of digits that are certain, and then an additional digit, only one additional digit, that represents our estimation. This is called our uncertain digit. So, for instance, if we're measuring the length of this metal rod here, then we have markings on the ruler that we can use to measure every 1/10 of an inch. Why are we using inches? Let's pretend it's centimeters, because who uses inches? Now we can say that the rod is 1.48 centimeters, where the 1 and the 4 are certain numbers because there's a mark for the 1, and then there's a mark for the 4, 1, 2, 3, 4th little mark. But it doesn't quite get all the way to the 5th mark, and so I had to sort of guess how much closer is it to the 5th mark than the 4th mark. And because that's a guess, then the 8 that's in the 100th place is called an uncertain digit based on the ruler that we have. Now, if you have other kinds of markings on your instrument, you'd have fewer measurements. So these are called significant digits in a measurement because we know them with enough certainty to say that it's accurate. Exact numbers are counted as significant, and they would have unlimited sig-figs. So like if we're counting the number of soccer players out on the field, we would count whole numbers as unlimited sig-figs, because you would never have like 1.5 soccer players. That would just kind of be freaky, right? And then all other non-zero numbers are significant. So all the digits you have in a measurement except for 0 are significant. Some zeros are significant and some zeros aren't. So we have rules to decide which zeros count. So first of all, we know any zeros that come between other significant figures are significant. They count as significant. Any zero before the first number does not count. After the last number, the zero counts only if it comes after a decimal point. And the decimal point is written in. So we have a rule to help us decide that we call the Atlantic and the Pacific rule. So in the Atlantic and Pacific rule, you have to consider a map of the United States and which side is the Pacific Ocean on and which side is the Atlantic Ocean on. So the Pacific Ocean we find on the left side of the map. The Atlantic Ocean we find on the right side of the map. Remember this rule because we're going to use the P for Pacific and the A for Atlantic to help us decide when does a zero count as a significant number. So here's what we're going to do. In a number like 3200, we're going to draw a line according to the Atlantic and Pacific rule. We're going to fly our airplane in for the Pacific, which was on our left. If the decimal is present, P for present and P for Pacific, then we fly in from the left. But for the Atlantic part of the rule, if the decimal is absent, A is for Atlantic and A is for absent, then we're going to fly in from the right side because the Atlantic Ocean is on the right side of the map. So in this number, the decimal is absent, right? There's not a decimal in this number. So we're going to fly in from the right and stop when we hit a non-zero digit. So now it's easy to see how many sig-figs there are in this number. 3200 has only 2 sig-figs because we crossed out the 2 zeros that do not count. They're just placeholders. They're telling us that the 32 is in the hundredths place in the number. They're placeholders, not meaningful digits. Now look what happens. If I put a decimal behind there, if there's a decimal there, then I'm not flying in from the Atlantic side. I'm flying in from the Pacific side because a decimal is present. So I fly in here until I hit a non-zero number and bam, there's one right away. Since there's a decimal present, that changes everything. So now I know that this measurement is accurate to 4 sig-figs, not just the first 2. So another example, same numbers, but now I've moved the decimal to a new place. Look, it doesn't change though. I fly in from the Pacific side because a decimal is present. So now I count all of these digits as significant. That means my instrument can measure to the 10th place, and it's more accurate than a measurement like this that only measures to the 1's place. So that decimal right there allowed us to use the Pacific rule and identify that a decimal is present, so we fly in from the left. So let's practice. How many sig-figs do the following numbers have? Here we have a decimal present, so I fly in from the Pacific side, and right away I hit a number, so I know there's 4 sig-figs here. So a decimal is present, so I fly in from the Pacific side of my page, and I go until I hit a non-zero number. The first one I get to is the number 7. This number has only 1 sig-fig. On my next one, there's no decimal. The decimal is absent, so I'm flying in from the Atlantic side until I hit a non-zero number. The first one is the 8, and so I have 2 sig-figs in this number. Here a decimal is present, so I'm going to start from the Pacific side, and I smash into a non-zero number right away. So 3 sig-figs here. Same is true for trial E. Smash into a non-zero number right away, so this has only 3 sig-figs. On this one, I have a decimal present, so I go from the Pacific side, and right away I hit a non-zero digit, so I have 4 sig-figs in that number. So that measurement is accurate to the 100th place. In G, I have a decimal present, so we're coming from the Pacific side, and that means everything here is significant. So I am measuring to the precision of the 10th place here. So telling how many sig-figs is the easy part. Doing the math is when it can be tricky. So let's not get confused. If you have multiplication or division, then your answer can only have as many sig-figs as the least number of sig-figs in the problem. So for multiplying and dividing, we're counting sig-figs, not decimal places. So if I multiply 1.31 times 2.2, I get an answer of 2.882. That's what my calculator says. But this number has 3 sig-figs, and this number has only 2 sig-figs. So I don't get to keep all of these digits here. I only get to keep 2 of them. So I have to stop after 2.8. The problem is I need to round appropriately. Since this 8 is greater than 5, that means I have to round this up. And it's going to be 2.9 is the most accurate measurement that I can give for this problem. Now if we're adding and subtracting, then the number with the least number of decimal places is used. So now it's not about sig-figs, it's about decimal places. So I add the 2 numbers together and I get 3.51. This one has 1 decimal place, and this number has, this number, the first one, 1.31, has 2 decimal places. 2.2 has only 1 decimal place, so I have to stop writing after 1 decimal place. I always look to see how to round appropriately, and the 1 is less than 5, so I don't round up. 1 decimal place is allowed, so my number that I can report with accuracy is 3.5. Now what if I have 3 numbers to add together? Don't get flustered, just add them. So let's see, adding, I'm counting decimal places, right? So 2.36 plus 1.7 plus 3.24, it's calculator time. 2.36 plus 1.7 plus 3.284. You probably don't need a calculator for this. And now let's evaluate, what do I get to keep in my answer? So in my final answer, how many decimal places do I get to keep? This has 2 decimal places, this guy has 1 decimal place, and this number has 3 decimal places. So this is restricting our answer to only 1 decimal place. I have to stop after 1 decimal place. So the most accurate answer that I can report is 7.3. Anything else after that is considered calculator vomit, because my calculator will spit it out for me, but I don't need to keep it. Vomit does not belong on your chemistry papers, please. Thanks. Okay, now we're multiplying. So instead of counting decimal places, we're going to count sig-figs. So you want to multiply first or do sig-figs? Doesn't matter. All right, I'll multiply first, then we'll count sig-figs. So I take 1.89 times 2.03 times 3.277. And my answer is a whole big long string of stuff. Wait. So what do I get to report in my answer? Let's see, this number has 3 sig-figs. I was almost about to count decimal places, but I know better. So 3 sig-figs here, 3 sig-figs in the 2.03, and then this one has 4 sig-figs. So we're restricted to the least number of sig-figs in our answer. That would be 3. So 1, 2, 3. I have to stop writing after the 5. So I look behind the 5 to see, how do I need to round? So I notice that this 7 is larger than 5. I round this up to 12.6. Okay, what if we're dividing? Well, multiplying and dividing have the same rules. Since this number has 2 sig-figs and the 3.74 has 3 sig-figs, then I do my normal division, 8.2 divided by 3.74, and then in my answer, I'm restricted to only 2 sig-figs in the answer that I get to report. So let's do the math. 8.2. 8.2 divided by 3.74. 2.1. Ooh, that's a lot of digits that I don't need. 2.19. I am restricted to 2 sig-figs. Okay, so here's my whole entire answer, but I only get to keep 2 sig-figs because 8.2 restricts my answer. So this is the measurement we made with the least precise instrument. I cannot be more precise in my answer than what my least precise instrument allows for. So the 9 is of course bigger than 5. That means I have to round up that number to 2.2 to report in my data. All right, now it's your turn. I want you to give these a try and type them in as answers on the quiz. Thanks. We'll see you guys in class.